In this video, we'll be covering wave-particle duality, which is another aspect of the behavior of light. So in a previous video, we said that light has wave properties, right? Light is a wave, it's speed, so when I switch from air to prism, the speed of the light gets altered by the medium, and each color of light is a different speed, so we bend and separate colors. Particles don't do that, right? A rock does not bend when I throw it into water. Light undergoes diffraction and interference, right? Light waves bend around edges, and so because of that, the crests and the troughs of those waves reinforce each other. They add to get bright spots. They cancel each other to get dark spots. Particles don't do that. If I shoot a BB gun at a screen with holes in it, some particles get stopped, some particles go all the way through. And so because light behaves like the top ones, we said that it's got to have wave properties. However, at the end of the 19th century, so late 1800s, early 1900s, a few experiments started showing us that that can't be the whole story. The first experiment was the idea of blackbody radiation. And there are several different versions of blackbodies, but a simple one is the coil on an electric stove. When I heat it up, so when I run electricity through it, it heats up and I see a characteristic color. The hotter it is, the whiter it is. So the center part's a little warmer than the outer part. But the thing about the blackbody radiation that was interesting was that the experimentalists were seeing this kind of shape for the light that they got out. They measured, how much UV light, how much visible light, how much IR light they got, and they found that it always had this peaked shape to it. That was odd because the theory, where they said light was a wave, predicted that it should always keep going up. As the wavelength got shorter, they should get more and more light of that kind. So there should be lots and lots of UV, not very much visible, and very little infrared. But instead, they saw this peak shape, so it actually tailed off at a certain point. And they really were unsure as to what was going on there. And so at the start of the 20th century, about 1903 or so, Max Planck, a German scientist, came up with a theory to explain this, and he didn't know why he was doing what he was doing. He called it his act of despair, in fact. He said that the atoms that formed the blackbody were vibrating, they were oscillating, and each oscillation had a certain quantum of energy associated with it, and that quantum, which he called delta E, was equal to some constant times the frequency of that vibration. Similarly, we saw stuff going on with light waves and how they interacted with metals. There's an experiment called the photoelectric effect, where you can shine ultraviolet light on metals, and that ultraviolet light is capable of pushing electrons out of the metal, which flow around the circuit, and at the other end, we can measure the kinetic energy based on how fast they were going. And that kinetic energy, they found, was related to the frequency of the light. As the frequency got higher, and remember, that means as the wavelength got shorter, the electrons that got pushed out by the light moved faster and faster and faster. But what was really interesting was that there was a certain frequency that they called the threshold frequency. If you were too small, nothing happened. The bigger you got after that threshold frequency, the faster the electrons got. And that was something that they weren't sure how to explain, and they couldn't explain with just the wave model of light. And so a really smart guy around the same time as Planck said, well, that must mean that light is composed of photons, right? A photon of light is a single packet of light, and those photons have energies. By the way, they match up with energies in the atoms, so he's tying back to Planck's theory. And the other thing he said was that the energy of a photon was equal to Planck's constant times its frequency. But the basic take-home behind all of this is that because light acts in a way that just the wave theory can't explain by itself, light also has some particle properties to it. And so I'd like to return you to the electromagnetic spectrum. In our last video, we said that there was a dispersion relationship that took the speed of the light wave and related it to the wavelength and the frequency. We now know that because light has particle properties as well, that there's a photon of light that has energy related to Planck's constant, which has this value, times its frequency. And because of that, because both of these equations are tied together by the frequency, we can make a relationship between the wavelength of light and the energy as well. So all three of these equations are going to be useful to us in describing the three fundamental properties of light: its wavelength, its frequency, and the energy of a photon. And so now we can add a little bit more information onto our light calculations. So we can turn wavelength into energy, for example. Right? We know that wavelength is equal to hc over lambda. So here's my Planck's constant. Here's my speed of light, and I'm multiplying those together. By the way, we can see that seconds will cancel seconds, so that's good. And then hc over lambda. And if the speed of light has meters in it, my wavelength had better be in meters, so I took that 650 nanometers and I converted it. Meters cancel meters, seconds cancel seconds, and I'm left with joules, and joules is the right energy for light. I've now found the energy of a single photon of this 650 nanometer light.